In this exercise, we're going to look at the glucose control in a type 1 diabetic patient. Diabetes affects a lot of Americans every year. You can see right here, and it's only increasing as far as trajectories show. One of the things we want to look at is that with diabetes comes this inability to regulate insulin within the body, which then regulates blood glucose. We want to maintain our blood glucose levels within our patient and within a healthy range. We have that defined here as between 64 and 104 milligrams per deciliter with a target of 80 milligrams per deciliter. We've discussed in control how these tuning correlations are kind of rough starting points, but they don't actually reflect what our final decision is, and that depends on the system. A good example is here that blood glucose values are out of range or undesirable, but values that are too low are much more serious and can lead to hospitalization or death if left untreated. And so these low values, we want to make a special concern that they don't happen. And so as we evaluate, that's where we as engineers will look at a holistic picture of how this is applied rather than just having some general rule of thumb that we have. We start with the general rule of thumb, and then we move on to specific cases. We also have some specific bounds for our input. Our input is going to be insulin coming into the system from the controller. That will then become remote insulin, and then that remote insulin will affect the blood glucose within the system. Let's go ahead. Let's first just actually look at our diabetic function, which will simulate the diabetic patient. We have a couple inputs. Those inputs are the insulin infusion rate and the meal disturbance, which is in millimoles of glucose per liter minute. Then we have this Bergman minimal model to include meals and insulin. We look at the states here. These are the 6 things that are integrated. We have the blood glucose, remote insulin, and the insulin within the system. We then have 2 quantities which are they're integrated, but we don't use them in a direct way. Rather, they both combine to affect this gut blood glucose. Gut blood glucose. I don't know why that's so hard to say. So we'll integrate those values as well. They'll help this system. This system has lots of integrating parts. It's not strictly a first order problem, as we have these different integrating parts affecting one another. We have some parameters, some constants that will affect our system as well that have already been regressed for us. So instead, we'll go ahead and we'll have a new vector for our output. Each one of these indices corresponds with the derivative of what is up here. So for example, the change in our glucose corresponds with some P1 times the difference between glucose and gut blood glucose, as well as relation with the remote insulin and glucose. F times absolute times Vg seems to be some constant relation. Gut glucose, and we have this, which corresponds to D. If we come all the way up, you'll see that D is our meal disturbance. We'll have similar equations for our remote insulin, our insulin, and then this Q1 and Q2 rate of change, which will affect finally our gut blood glucose. We'll make sure this is a column vector, and then we'll return that column vector so it can work with ODE45 and other integration functions. So the first thing we want to do is develop an FOPDT relation, so we have some idea of the dynamics of the system. We have our initial conditions for each of those states, as well as the initial condition for our insulin pump and the meal disturbance. And we'll go ahead and we'll simulate this for over 24 hours. We'll store our values for the blood glucose, remote insulin, and the insulin. That's just the insulin given by the controller within the system. And we'll simulate with ODE45. As we look at the effects here, we'll see that we have the initial state of glucose here. And as we change from an insulin pump level of 3 microunits per minute to 2, you'll see that glucose increases up to, it looks like, about 110. Our insulin similarly decreases as the pump rate decreases. So if we remember, our insulin affects the insulin within our system and the remote insulin, and that remote insulin then affects the blood glucose. So let's look at how we regress our FOPDT model. We have our change in U, which is -1. We're going from 3 to 2. Our dy is going to be the G, the glucose, at the end, minus the G initial, and that's going to be our dy. And that will give us our gain, dy over du. Our theta p we're going to say is roughly 0. That's just a guess. And our tau p is equal to 2 hours, and that's the time it takes to get about 63% of the way there. From that, we'll obtain rough PID tuning constants. We're going to use an IMC tuning constants. So our tau c is going to be the maximum of 0.1 times tau p, or 0.8 times theta p. Kc then comes from this relation. Same with tau I and tau d. So we have these IMC tuning correlations. These will give us rough ideas of where we should start, and we'll go ahead and we'll print those as well. We also have this derivative filter here. This derivative filter here will help us filter out measurement noise so that our derivative term is less sensitive to this noise and enables us to just focus on changes within our derivative that are meaningful. This works by being multiplied by our derivative term within our PID equation. So that will be an extra term we calculate here as well. So we're going to implement our PID controller like we've done before. We'll initialize our states, our constants. Here we also have meals, and these meals will be added to the already existing disturbance baseline that we created before. And so now the meals will change with respect to time. You know, we have meals throughout the day, and so we iterate through and we add those meals to our system. Then we have our PID arrays, and so that's where we'll store error, integral of error, derivative of the process variable, as well as the P, I, and D terms. We have our upper and lower limits, and then we're going to go ahead and loop through. We calculate our delta time, our error, we get the derivative and the integral of error, if we can, and then we create our proportional, integral, and derivative terms. Finally, we go ahead and we put these all into our PID controller, and we implement the derivative filter as well. Then we do anti-reset windup, and we clip the output if needed, and then we simulate it, again, using our diabetic function. We'll go ahead and if we make our plot a little bit bigger, we can look at the results. So you can see breakfast definitely does, lunch and dinner, they cause, almost looks like a heartbeat, where we have an increase in glucose, followed by a decrease, and that decrease is because our insulin pump increases to the point where we kind of have a little bit of overshoot to get back down to that set point. Similarly here with lunch and with dinner, we have similar shapes where we spike our remote insulin and our insulin so that we're able to adjust for that effect of the glucose. Our proportional term will get larger here. The same with our integral, and then our derivative will try to balance that oscillation out, but our proportional term is there to cause that large increase proportional to the increase in error. So we'll go ahead now and we'll discuss tuning. So we'll tune our PID controller. We'll think about what would be best here. My thought here is maybe a little bit less of a Kc and a little bit more of a little bit less of a gain, but more integral control may help us, for example. So we can go ahead and we can change that a little bit. We had our initial constants up here quite a ways. So our Kc was -2.8, tau c was 0.2, and tau I was 2. So if we come down here, rather than use those correlations, we went ahead and just, our Kc is a little bit lower. Instead of 2.8, it's 2. 0.5 is our tau I, and our tau d we have here. Our tau d ends up being 0. So let's go ahead and let's see how this system works. Same thing where we still implement it in a similar fashion. You'll notice we have a little bit less offset, but similarly, actually go ahead and just run it. Just make sure everything's the same. Yep, so what we do here is we that's what tuning is. We start looking at things. This low, for example, that spike that's low, is more dangerous than high spikes, for example. So what we could do maybe is No, let's change our Kc to 4. And let's change our tau I to 1. That's in between where we were before. And we'll go ahead and we'll run the section. So we have more oscillation. We still loop low, which I don't love. What if we implement derivative control? What would happen then? So we'll go ahead. Our tau d is 0 right now, so we'll go ahead and we'll comment out this relation. We'll say tau d is equal to 1. We'll run the section again. And now we go way up. Our system is unstable, that's for sure. That's due to that gain. That gain will usually cause instabilities. Let's change it to 3 and see what happens. And we're still unstable. Obviously, this would not be ideal for our system to reach glucose levels that high. So go ahead, we'll change it to negative 0.2 again. Our tau I will leave at 0.1. And we'll get rid of our derivative control, see if that helps. We outputting some, must be output some in the next one. So we'll come back up here. I'm going to go ahead and just take these constants we had before. Kc is now negative infinity up here. That's interesting. That would cause a lot of instability. So we'll go ahead. Sometimes what I've seen is that things that happen before affect our C. So let's go CLC clear all, close all. So now we have a fresh system. What I think happened is that we ran some things a few times, and so they affected one another. So we're going to go ahead, just run our sections from the start. There's our step test. We go ahead and we fit some parameters. Kc is still infinity according to this. So let's look at that. Kc is coming from this right here. Kc is equal to tau p. Let's run this again, make sure we have it. Yep. So tau p, theta p is equal to 0. Kp is equal to 0. That's not right. So why is our Kp equal to 0? dy is, okay, let's do n minus 1 right here. That's why our dy is all wrong. We didn't assign the last one just by the nature of our system, but we assigned the second to last one. So we want to make sure, let's make sure our dy is still 0. So glucose, let's just think about things for a little bit. How many steps do we have? We have 24 times 6. So right here, our NS is equal to 145. So let's just say we reach steady state at 140. We'll go ahead and run a section. Now our dy is equal to 36. That's more like it. Our Kp should be about negative 36. Theta p equal to 0, tau p equal to 2. And we get these constants. Tau c is equal to about 0.2. Kc is equal to negative 20.27. And tau I equal to 2. We could also print our tau d. Our tau d looks like it ends up being 0. That's because our theta p is 0. So we'll go ahead, we'll implement our PID controller now. Hopefully we get better solutions now that our Kp is not infinite or 0. So you can see we still have those oscillations as we saw before. And we're going to go to the tuning section now. Kc is equal to 0.2. Let's say that's negative 0.25. tau I is equal to 1. Remember, as our tau I becomes lower, its effect is felt more because it's on the denominator. Now we have a change. Slight spike. Let's go ahead and maybe set that equal to 0.5. 0.5. Run the section. Have more oscillation, but we don't see a greater degree of change. Let's set our Kc now to -3. So we had an instability happen last time we did that. So I hope you see now that this is all a little bit of trial and error, but we need a good understanding of our system to do so. And we'll see we're just getting more oscillation. That's not ideal. The one thing we'll try is implementing some derivative control now. Let's set our derivative term to 2. We'll go ahead and we'll run. We're now running from the start on accident because I hit the wrong button. But this is fast enough. And we have that instability we saw before. So we'll go ahead, we'll just set 2.5 and tau d equal to 1. And one more try. Alright, so we're going to go ahead, change it back to what we had before. We had some pretty good initial constants. And the last thing we'll do is we'll manipulate it a couple times. So let's set this equal to -2, tau I equal to 2, and tau d, let's leave tau d at 1 for a moment, see what that's like. Let's set tau d equal to 0, and see what that's like. Maybe it was tau d all along that's causing all the problems. Okay, we're a little bit too high. Last time we had it a little bit lower, so I'll go ahead one last time. We'll adjust these constants. You can see how sometimes we like those sliders. Those sliders are kind of nice. A little bit lower. You can see we're trying to just get those peaks, especially that peak right there is what concerns me, that we're going too low. So we'll say 0.5. Run section. Still don't love that, but we're getting lower there, so I do like that. And maybe what we do then is we implement a little bit more, so like 0.28 like we had before. So you can see it's just playing around, observing the effect. If we set our integral control, let's try setting our integral control to 4. See if that, doing the opposite of what we've done. Actually, I like that. So we see this is now hemmed, and they're both hemmed in a little bit more. So let's run with that for just a bit. We're going to come down. We see a response. Now we're going to generate some tuning sensitivity guides. And what we're going to do here is we're going to run 6 cases. We're going to double and then half the best Kc. The next 2 cases should be use the best Kc and the best tau d, so the best process time. But should use double, then half the best process time constant. Or tau I, excuse me. We're not adjusting the values. We're adjusting the PID controller values. So you'll see we'll go ahead and we just set the constants here to 211, 0.511, 111. And what we're doing here is we're changing what everything is multiplied by. We multiply our constants by that value for each of these 6 cases. Then we go ahead and we simulate the cases as before, and then we plot them. So we have 6 of these plots, you can see, and we'll go ahead and run it. Just make sure we have the most up-to-date values. I noticed right here, I'm going to fix this while it's running. The tau I and the tau d are formatted wrong. So we'll just do \tau_I. Okay, let's look at our plots. So here's a Kc that's half of the previous value. And you'll notice we actually do pretty well. Our tau I as well is 0.5, our tau d is equal to 1. And you'll notice we stay very clear of that bottom portion there. Let's compare that to a KC that's double. And you'll notice we have that, now we have that port problem where it comes up and above, that overshoot that happens. So that's half, I should say. That's much lower. So we because of that much lower change in our gain, we don't respond quick enough to those spikes in glucose. So keeping our Kc at 0.55, which was the best. Let's look now at our changing our tau I and our tau D. This is tau I of 0.1, twice the value, and our tau D of 0.25, so half. You'll notice some more oscillation when the tau I, so the integral control, is more impactful, and we still have these spikes. So we'd rather not have those oscillations, and so that's what happens when our tau I is too low. We have some oscillation. Similar with derivative, here's twice the derivative control. Here's half the derivative control. You notice with half the derivative control, we have a higher spike yet again. With double the derivative control, we don't have the spike. In fact, it impedes the spike quite a bit, but we do see some oscillations here at the end. So that's where the derivative control changes things. So hopefully, especially the sensitivity experiment gives you a good idea of how different parameters affect a system, as well as how our system will respond to disturbances. Here, those disturbances come from meals. Please let me know if you have any questions. Hopefully this was effective.